now it's time for moving the next talk from Elena Asencio, also Bond University. The talk is on current problems of LambdaCDM on large scales, El Gordo galaxy cluster, and the KBC void.
The talk is on the current problems on LambdaCDM on large scales. So you probably have heard many times that LambdaCDM explains the large scale structure so well, and it's such a successful theory on these scales and all that stuff. But actually, LambdaCDM has many issues on large scales. So, for example, one of these cases in which LambdaCDM has a problem is on explaining El Gordo galaxy cluster, a supermassive galaxy cluster at redshift of 0.87. Another example would be the KBC void, which is a very, very large void or underdense region between 40 and 300 megaparsecs around the local group. And of course, there is the very well-known Hubble tension that you have probably heard about. So to start with the first example, El Gordo is, as I was saying, a supermassive galaxy cluster at redshift of 0.87, formed by two subclusters, which have a total mass of 2.13 times 10 to the 15 solar masses. Now, this is a very, very large mass for LambdaCDM expectations. So in LambdaCDM, if you take a simulation and you ask the simulation at redshift about 1, okay, give me the most massive extreme object that you can possibly find in the simulation. So the LambdaCDM simulation would form objects of maximum 1.7 times 10 to the 15 solar masses at this redshift. So significantly lower than what we're seeing here. So that's kind of a problem for the theory. But the thing is that that's not where LambdaCDM problems end regarding El Gordo, because El Gordo is also known for being one of the hottest, most X-ray luminous and brightest galaxy cluster at this redshift. And this implies that in order to make this very high temperature and very high luminosity, the two subclusters must have collided at a very, very high inflow velocity. So at about 3,000 kilometers per second, which is, again, a lot higher than what LambdaCDM expects. So in LambdaCDM, one would expect these objects to collide at maybe 1,000 kilometers per second or even less. So if you take into account the very high mass and the very high inflow velocity, you find that El Gordo is an object that is in more than 5 sigma tension with LambdaCDM. It cannot possibly be explained by this paradigm. And then from this, one would perhaps deduce that in order to explain supermassive objects like El Gordo, structure formation would need to be more efficient than LambdaCDM predicts. Now let's assume this statement is correct. If structure formation is more efficient than we expect, then the matter would aggregate into these supermassive structures easier, and therefore this would leave gaps or underdense regions where the matter used to be. And the funny thing is this, such underdense regions have indeed been observed. So a local underdensity has been observed in several wavelengths, so in optical, in radio and X-ray and near infrared. And among all these studies that are mentioned in here, the one from Keenan Barger Cowie of 2013 was the one that found stronger evidence for an underdensity. So what they did in their study was they sort of counted galaxies and they observed their distribution in the surveyed volume. And what they found in this study is that the density was about 0.5 times the cosmic mean, between 40 and 300 megaparsecs. So to be a bit more specific, the density in this very large region has a density contrast of 0.46 as observed. This is a lot higher than what LambdaCDM predicts, because from LambdaCDM we have the CMB constraint that tells us that the expected density fluctuations should only have an amplitude of 3.2%, so 0.032, like a lot smaller. So yeah, that's definitely another problem for LambdaCDM. So maybe from this, maybe it's easy to see how the El Gordo problem and the KBC void problem are related. But then maybe you are wondering, what does this have to do with Hubble tension? So these problems are perhaps and probably related to the Hubble tension, because I don't know if you ever heard the possibility that the H0 anisotropy might be caused by bulk flows. Now, what is a bulk flow? So bulk flows originate when local matter inhomogeneities lead to a stronger gravitational pull from the underdense region towards the denser one. So the matter in the underdense region feels the gravitational pull of the denser region, and this makes it move towards the denser region. So this stronger gravitational pull would appear as if the universe was expanding at a different rate in the inhomogeneous region, and thus leading to the observed H0 anisotropy. So it looks like the universe is expanding at different rates, but it's just this pull from the underdense towards the denser region. And well, just to clarify, these bulk flows are not just a theoretical construct. These bulk flows have indeed been observed and studied in several studies. And as to whether the observed bulk flows matched the observed under density observed by Keenan, Barg, and Coe. So the answer is, well, the answer was given in a very recent study, and well, it has previously been studied in Hasselbauer also. But very recent studies show that for causal and exponential profiles for the density, you can qualitatively match the bulk flow curves, which, yay, that works. So just to summarize, we have three main problems that I wanted to talk about today, which are El Gordo and the KBC void and the Hubble tension, which all seem to point to the fact that structure formation does not work like the standard model predicts. And well, I also wanted to mention that I focused on 3 cases because I just had 10 minutes and didn't want to run out of time, but there are like so many other things pointing to the same conclusion. Like, for example, one would see different star formation rate densities in local and global universe, or just to mention that El Gordo is not the only supermassive galaxy cluster that has been observed. Like, it's a problem for the CDM. Like, there have been many other supermassive galaxy clusters that also have problems. There's also the fact that 1 gigaparsec arc of galaxies and galaxy clusters has been found at 0.8. That's also very hard to explain with the current model. And of course, as we were mentioning before on Pavel's session, the preliminary James Webb Space Telescope results also point to the fact that structure formation is a lot more efficient, because otherwise we could very hardly explain, or we could not explain, these very early and massive galaxies forming so close to the Big Bang, say, somehow. So yeah, that's all I want to say for today.
I just want to mention that, like, there's a more recent study by or discovery by Lopez of like a ring of galaxies at redshift 0.8, which is similar to what Eleanor's talking about. It's more recent. I think that hasn't yet been peer reviewed.
Yeah, actually, I was discussing it with Robert yesterday.
Yeah.
I mean, I didn't include it because I couldn't find the paper.
Yeah, I don't think it's been peer reviewed yet.
But yeah, I also saw that, and yeah, more problems.
Well, I think it's more a sign that you need enhanced structure formation, probably. But it's the 2022 paper. I believe the methods used this time around are similar. It's worth looking into, like how. I mean, to analyze it statistically, you probably do something like quantify the length of the arc versus the redshift, and see in that 2D parameter space, like what's the expected distribution, how much of an outlier it is. I don't know if anyone's done anything like that.
do you think that is possible with only one fundamental assumption, the revision of one fundamental assumption could resolve most of the problem in cosmology, or we need several corrections of the fundamental principles?
So, well, in general, in my talk, I was making a strong point towards the fact that the main problem here is that structure formation is not efficient enough. So that could be seen as one thing, but it's not like one could easily solve that in the standard model. Like one cannot just say, okay, so now we make structure formation more efficient and everything is solved. Like you would really need to revise the whole paradigm, I think, in order to fix this problem in the standard model. So even though it looks like one problem, it would need a very complex solution within the standard model. So it's not just one thing, I would say.
Mm-hmm. And the alternatives is tested with the same observation to check if works well for the same issues.
So about alternative models, you mean?
Yes, the MOND and relativistic MOND or other modified theories.
So in general, I would say it's hard to answer these questions without having actual simulations. And up to now, the only like detailed simulation that has been done in terms of MOND, which would be the alternative model, was the one with sterile neutrinos that Pavel was also commenting about. And one does see that with MOND, it's a lot easier to form these structures. So El Gordo or the bullet cluster or the supermassive clusters or the void itself, they are easy to form in this MOND plus neutrino cosmology. But as Pavel was also saying, it does seem that the neutrino, the sterile neutrino plus MOND model also has its own issues. So I think we still need to keep testing more models and see how that goes.
Okay. More questions here. I think is
some comments on chat, maybe. Yeah.
Comments. Yes.
Maybe.
So, yes. Okay. Yes. So, Frederic.
Yes. Maybe it's not a good question, but sorry if it's maybe it's a ridiculous question. But you told us, thank you for the presentation. You told us about simulations. Okay, so I understand. I think simulation of MOND and LambdaCDM. And do we have also, apart from these simulations, equations? For example, I suppose in Newtonian, pure Newtonian regime, it would be a sinusoidal curve. I'm talking about the density curve, the resulting density curve, which should expect, for example, today in the different models. In the Newtonian model, probably, I don't know exactly, probably there is something like a sinusoidal curve which describes the density distribution of today. In MOND, maybe it's different. In LambdaCDM also. Okay, in surrounding, maybe I can talk about something. I have a very exact equation for that. So that's why I asked this question. Thank you.
So I don't know if I fully got the question, but I mean, as to whether we have the equations. I mean, like I said, I do think it's hard to give a clear answer without simulations, because in order to form these objects, like you need to take a lot of things into account, like for example, for the simulations that have been used for LambdaCDM or the neutrino MOND simulations, like you always start with a background cosmology, like usually given by the CMB, and this will give you how the systems will evolve, and how they affect each other. So I think it's a very complex problem. So of course, the theoretical equations or just the math can give you some insights, but I think it's hard to know unless you do the actual simulation. But yeah.
Okay, thank you. Yes, I think you understand very well my question. Thank you very much. Thank you for that. Okay.
Okay.
Maybe
I have.
Can I just add just a quick statement to Frederick, and that is that if you have a model which tells you the average density in the universe as it evolves, right? The observations can deviate from that if over and under densities form. So we can be in a major underdensity and see only a fraction of the matter around us that would otherwise in an analytical calculation be there. So this is something one has to take into account.
Okay, so it's not so simple. Thank you.
Yes, indeed, I think that also a key point is the most effective force of the MOND theories for low accelerations. With these more effective interactions, I think is evident that the structures grow faster than the standard gravity. Yes?
I would like to. So one question was that can MOND or modified gravity correctly address the Virial theorem in clusters? Like the Virial theorem does change in MOND type of gravity, or it remains same? Anything?
So
Anything with Virial theorem?
So I mean, yeah, the Virial theorem does look different in MOND in the sense that the equations change. But are you referring specifically to this paper that talk about this, or is it a general question?
Yeah, it's just a general question, like
A general question.
for MOND type of gravity, like what are the changes?
Yeah, I mean, like when you introduce a different equation for gravity, of course, your equations are going to change. Okay. But yeah, I mean, as far as I'm concerned, this is something that works.
May I comment?
Yes.
Yes.
So I mean, like Indranil was saying, like the concept is the same, but of course the potential energy will change because your equations have changed in terms of the gravity.
Yeah. Asher wants to say something.
Yes. You see, the Virial theorem depends on Newton's third law. And if you take into account retardation, Newton's third law does not hold. That's obvious. And therefore, you need to put some correction to the Virial theorem if you intend to use it on the scale that people use it. I mean, on scales of a galaxy cluster, which is a few megaparsecs.
Can I address this? Is that okay?
Mm-hmm.
Yes.
Yeah. So the retardation effects cannot really be very significant because, for example, when the Earth's orbiting the Sun, the position it sees the Sun is sort of delayed by 8 minutes, or they're retarded by 8 minutes. Now, if the force of gravity on the Earth due to the Sun was towards where we currently see the Sun, as opposed to where the Sun sort of instantaneously is, then the Earth would spiral into the Sun in only a few thousand years. So it's sort of understood by now that basically what happens, the Sun sort of depresses the space-time fabric, if you like, or distorts it. And this obviously happened sort of billions of years ago, and it's created a steady state pattern in the fabric of space-time. And the Earth is like a test particle moving in that, right? So at any moment in time, the gravity on the Earth is towards the instantaneous location of the Sun, rather than where we see the Sun on the sky. So because of this, the retardation effects, of course, would, if they existed, would in principle be more significant in a galaxy cluster. But we already know that that's kind of not how things work, essentially.
Well, I can respond to this by saying that you are correct regarding the solar system, and if you read perhaps my paper on Mercury, you would have seen that, but it's not true on every scale. The solar system is so minute with respect to galaxies and galaxy clusters that it's a totally different scale, and things are affected differently on different scales because of retardation.
What do you think about universe linearly expanding at the speed of light? I mean, the Hubble horizon coincident with the Hubble radius coincident with the horizon.
Yes, I think it's a question for the second session.
I think Roberto and the others will address specifically this in the next session. So maybe it's better if.
Yes.
I wanted to know your opinion simply.
Oh, my
your
opinion,
Elena. Okay.
Okay. No, I mean it's. I think it's a very striking coincidence how well the data matches the expectations for a linear expansion. Like it's a very surprising coincidence, I would say. But yeah, like and to be fair, I'm not a cosmologist, so I don't know what's exactly going on. But yeah, I mean, I do think it's something that it's interesting to look up in more detail, and that yeah, definitely a possibility, I would say.
Thank you, Elena.
Perfect. Yes, I think the idea is to solve gravity for all scales, for galaxies and the cosmological scale, without the use of dark matter and dark energy. So the linear expansion is one of the possible solutions that are compatible with MOND. And it's possible to work with dark matter in both scales. I think so.